So welcome to the last part of lecture 22. In this last part, I want to prove kind of the next theorem, which says that if I take any operator over the complex numbers, and if I know its distinct eigenvalues, and I know the multiplicity of each of those eigenvalues, then I can find a basis of V such that the associated matrix is a block diagonal matrix. And not only that, I know that each block has a particular form. AI has to be a DI by DI matrix, where DI is the multiplicity of lambda I, and lambda I appears on the diagonal DI times. And then this is an upper triangular matrix. So you want to think of each of these AIs as being upper triangular matrices. So if you think back at kind of what we've been trying to do in chapter 8 is we're trying to find bases so that the associated matrix has lots and lots of zeros. So we're getting there, right? Because now what this theorem is saying is you can find now matrices, all that are upper triangular, such that you can find a basis such that all of the matrices that show up here are upper triangular, and then you have big blocks of zeros. Okay, so if I go back over to the example, here could be a potential matrix associated to a basis, but actually we would want all of these kind of lower parts to be zero. So we're getting close. We're filling up lots and lots of the matrix to be zero. Okay, so how does this proof work? Well, we have to continue to use this new result that we have, that we can decompose our vector space as the direct sum of generalized eigenspaces. That's going to be a useful fact kind of going forward. And one of the useful facts too is you want to pay attention that given any operator, once you know an eigenvalue, you can break your your operator into the sum of two operators. Oops. Right? And so this is kind of like, the mathematician's favorite trick. We're taking an operator and we're kind of adding a zero operator, but we're doing it in a particularly nice way. Okay. Now we start kind of using all the pieces that we've done in today's lecture. Now this first part of the operator, when we look at it on the space lambda I t, it's nilpotent on that particular subspace. Okay, but so it's nilpotent on the subspace. So that means, right, from our last lecture that there is a basis of this eigenspace such that the matrix that we write, the matrix associated to this linear operator, if we restrict it to that subspace, has to have the following form. It has to have zeros down the diagonal. It has to be a lower triangular matrix, and there could be some non-zero things up there. And not only that, because my space is DI dimensional, this would be a DI by DI matrix. So what this part here is doing is we're using the result from last class, which says that any nilpotent operator on a space, its associated matrix has this form. Okay, and now the other thing that we want to note is that the matrix associated to the operator lambda I times the identity operator on the subspace will have the form lambda I, lambda I, lambda I, 0, 0 with respect to the same basis. Okay, and so what we then can do is we can take these two matrices and we can combine them to figure out what the matrix of the operator T is on this space, because we can just now take the sum of these two matrices and add them together, and we get that this matrix here is going to be lambda i's down the diagonal. We'll have some stuff up over here and 0 in the bottom left hand corner. Okay, but now what we're going to do is, so just to kind of just realize what we've done, for each of these GIs, you can find a basis for each of the GIs so that when you just restrict to the GIs, this is what the associated matrix looks like. But then what you want to do is we want to take all of these bases and put them together to form a basis for V. And then since T is invariant on each of those spaces, the matrix T associated to the operator T then is the matrix you get by putting in all of these little matrices that you found. So you have lambda 1 up to lambda 1. There is your first block. Your second block is lambda 2, lambda 2, and then with a star right here, and so on. We carry it all the way down, okay? And the reason that is because remember, these columns here are indexed by the row of the first eigenspace. So and because it's invariant, it has to pop in to be expressed in terms of these rows. These columns here correspond to the basis of the second eigenspace. It's because it's invariant, T is invariant under those elements. The outcome has to be expressed in terms of those basis elements as well. So all over here is 0, and all over here is 0. Now I realize that if this is the first time you're watching it, you may just be completely lost, okay? And especially because I've done it in kind of a very theoretical way. So what I will do in the next lecture is actually take a kind of a sizable example, and I will work out all the details so that you can see how I figured out what this particular block matrix is. So that is kind of where we are going to go for the next lecture. If this was confusing, maybe I would suggest is try watching the next lecture and then come back to this lecture and try to see what's going on in the proof. Now there's a bunch of key ideas here. First of all, that V has a basis of generalized eigenvectors over the complex numbers. So this is a very important result, and we saw it being used multiple times in today's lecture. We introduced the notion of multiplicity, and the other big thing that we did is with respect to these bases of generalized eigenvectors, what we're getting is an associated matrix of block. The associated matrix is a block matrix. Okay, so I know there's a lot going on there. I hope this kind of helps illuminate the material of section 8b, and I'll see you in the next lecture.